I had asked for a projector, but I guess I had crossed wires somewhere, so I don't. But this is today's agenda. I mean, not today's agenda. This is the agenda for the whole class. You should have it in front of your book, start your handout. And this is April 19th, so we're talking about radiometric dating. But to start with, you need to know a few things about elements and isotopes. Everybody's probably heard of heavy water. What is heavy water? Anybody know?
Yeah. It's made up of hydrogen, where the hydrogen atoms contain an extra neutron. And that makes that hydrogen twice as heavy as ordinary hydrogen. So,
have a cookie. Trying to reward you. You're right. And there's also notational things. Normal hydrogen. Make sure that I've got my. I do not wish to speak a falsehood, therefore I will double check. Okay. The superscript tells you how many protons. And the subscript tells you excuse me. This tells you the number of protons. And this tells you the I don't know what I'm going to call it. I believe it's protons plus neutrons. So hydrogen, regular hydrogen would be like that. Deuterium would be like that. Oops, no, come backwards again. I hate this. 1, 2. And tritium is like that. So if we just turn these into water, look at them one at a time. H2O has only one proton. H2O has a proton and a neutron. H2O with a proton and 2 neutrons, which would give you a total of 3. And heavy water is used in nuclear reactors because water acts as an absorbent of neutrons. It can go from here, eat up a neutron, eat up another neutron. And so it acts as a controlling mechanism for nuclear reactors. Well, that doesn't help.
It's interesting to note that heavy water is poisonous to human beings.
Indeed, because it will cause some radiation.
They can't use it.
Tell you what, I'm going to put my books down and invite you to come up during the break. Can anybody see this one?
It's in the chart.
Okay. If you can't, it's in the chart. This is the table of elements. And almost all of them you can see, like hydrogen has a 1 above it, lithium has a 3 above it. So lithium has 3 protons. And you can literally count. You can say hydrogen has 1, helium has 2, lithium has 3, 4, 5, 6, 7, 8, and so on. That's the number of protons in the nucleus. And the number of protons is also what dictates the number of electrons. And that means that there are electrons free to multiply and turn into molecules instead of atoms. These elements are all atoms to begin with as they're presented. And an atom is the Greek word for you can't cut, uncuttable, indivisible. And we now know, that an atom contains electrons, protons, and neutrons. And the neutrons and protons are made up of quarks, or quarks, depending on how specific you want to be. So the word atom no longer has that meaning. If you have nitrogen 15, I believe it is. Okay, if you start with normal nitrogen up in the air, it gets bombarded by cosmic rays. And what happens is it gets changed. Where's my note? It becomes carbon-14 with only 6 by emitting one of its protons. And since the radiation from the sun, the cosmic rays and so on, over long periods of time is relatively stable, that means that carbon-14 in the atmosphere is being replenished at an approximately constant rate. It can be argued, but if you accept that it's at a constant rate, what that means is every breath you take, every breath, quote-unquote, plants take, everything that has carbon in it will take in the same ratio of carbon-14 to its natural cousin, carbon-12. And carbon-14 has a half-life. Half-life is where for any given time period, 0, 1, 2, 3, 4, 5, half of what was there at the beginning is left at the end. So you get this kind of a curve because in the first hour or whatever, it goes by half. In the second hour, you have half, so it goes down to a quarter. In the next hour, it goes down to an eighth, a 16th, a 32nd, etc. in terms of the activity of radioactive decay. I listed things for you to tell you about the different kinds of radiation, but the main thing to look at is the nucleus of an element splits into 2 or more elements or particles. And that's what we're talking here, and we'll be talking about it in another way as well. Okay, I'm alive, I'm breathing in carbon dioxide, or breathing it out actually, but I'm getting carbon dioxide from the plants that I eat. I like to eat fresh plants, so over the millennia, my salad, which stayed in the fridge for a week before I ate it, that doesn't really matter compared to 100 years or 1,000 years. Because when I die, I'm no longer taking in carbon. I'm no longer taking in this ratio, whatever it may be. And then what happens is this starts decaying. And it has a half-life of 5,700 years. Does anybody not know what a half-life is? So what that means is if you were to take a Geiger counter to a piece of wood that had been buried at a dig, and you listen to the radioactivity, you can use the half-life of about 5,700 years to know how old the thing is. You have to handle it properly so there's no contamination. You have to be concerned about surface contamination with things like bacteria and fungi and so on. And, whoops, I promised myself. It is tricky to do this properly, but you can get results. And because the carbon is fixed in the body of a plant or an animal when it dies, if we dig up any kind of archaeologic site that has carbon material. Fireplace charcoal, for instance, the remains of a fireplace, that can have carbon in it. And you can say, okay, that piece of wood, by carbon dating, is X years old. And the way you do it is by this job. Where is it? Nope. Didn't get it. Look in your handout, and what you'll see is a gadget which has a big curve. And in the middle is a strong magnet. I don't know if it's an electromagnet or if it's a physical magnet. I think it's probably electric. So you can be specific about the actual radioactive field intensity. I mean, not magnetic field intensity. Then what you do is you add a little chamber here to inject your material, or to place your material. You put some flames over that, and actually they vaporize it by electricity. But what that means is the atoms lose an electron. So now they're charged. And if something charged meets a magnetic field, like an electric current, it responds. So what happens here is it will respond to that magnet by following it around. Now, Now, this is wider, or excuse me, this is adjustable. So that while you vaporize the stuff, you can adjust this, and you can see what comes out the other end with your detector, and it will tell you, essentially, you can tell which molecule, which atom is coming out at a time. And you can count the number of carbon-14s, because they're going to have to require a field strength of 1, whereas carbon-12 needs 1.03 or something. They'll be separated. That's the main thing to know. And you can count the atoms, or actually this is now plasma, or you can look just at the radioactivity of something and weigh the amount of carbon in it and get a guesstimate for that. But the mass spectrometer is a fabulous device. I've used it myself when I was doing chemistry in college, and you can just get these amazing readings where you'll have a line, and then you'll have spikes which tell you each one of these represents a different atom. And so you can even get ratios of atoms in a molecule. Okay, that's carbon-14. That only goes back so far.